day, students. The topic we are considering today is real and apparent expansivity. Now, what does it mean? Now, let's see. Real, use gamma R, small letter r, and gamma A for apparent expansivity. The expansion of liquid is complicated by the expansion of the containers. It is necessary to distinguish between the real and the apparent cubic expansivity of a liquid. When you say real, something that is original. When you see that it's not expanding more than how it should be, it's not faking it. Now, when you say apparent, let me assume you put a liquid inside a container, and as the container is expanding, you now assume that the water is expanding the way the container is expanding. By the time it comes back, it maintains its shape. That's apparent, it's not real. Let me say you put a stick inside water, it seems as if the stick is bending. It's like it's coming up. No, it's not, it's apparent. But the one that goes down to the bottom of the bottle direct is the real. Okay, good. Now let's now see what we mean by that. Real expansion equals apparent expansion plus the expansion of the container. When you put the water inside the container, let me say this is the container, you put water here. When it expands, the container expands, you now mix the water to, you now think as if, because this container expands, water is bigger than this because of the expansion of this, because more wide. No, it's not like that. It's the apparent. It's the apparent. Let me say you have a container and you put a stick inside, and it's now assume that it's bending like this, it's coming here. This is the apparent. This is the real depth. Real depth. Because this is the real stick, original. Why this one is the apparent depth of the stick. Now, when you have what is an experiment, you have relative density bottle. A relative density bottle, you weigh it with a spring balance when it's empty, when you have not put any liquid inside it. After weighing it, you now clean the mouth of the bottle and you fill it with a paraffin liquid. And when you fill it, the apparent expansivity of the liquid, that's the paraffin, that's what we want to look for, that's what we're in need of. Now, when you now put the paraffin inside it and you put the stopper so that it will reduce when you start heating it, because the experiment I want to heat it. When you start heating the liquid, you put water bait here, water inside. You want to be heating it, but before you heating the water, before you put the liquid inside the relative density bottle, and you weigh it also, know the mass of the liquid that was there when it has not started, you have not started heating it. By the time you weigh it, record the mass, and by the time you start heating it, there are some liquid that will be passing through the stopper. A little will be coming out until you start, after heating it to some extent, when you notice that no more liquid is leaving the relative density bottle, you now remove the Bunsen burner from the bottom of the container. When you remove it, clean the mouth of the bottle, and you weigh it again. We are going to get a formula that says to get the apparent cubic expansivity now, we have the volume of the liquid that got expelled when heating it, and volume of the liquid remained. There's no way all the liquid will leave the container, despite the fact that you put the stopper that will stop the liquid. There will still be some that will remain after heating it. That's volume of liquid remain times the temperature rise. Temperature rise means that before you start heating it, when you put the the relative density bottle inside the liquid, you take the temperature, initial temperature. When you start heating it also, you take the final temperature to know the temperature difference. Now, the apparent, the real or absolute cubic expansivity is definitely the same as the volume or cubic expansivity, which says is the increase in volume per unit volume per degree rise in temperature. And real expansion equals, don't forget, apparent expansion plus expansion of the container. That's the formula I put here. Real expansivity, cubic expansivity equals apparent cubic expansivity plus cubic expansivity. Now, the apparent cubic expansivity of a liquid is the increase in volume per unit volume per degree rise in temperature when the liquid is heated in an expansible vessel. This is the expansible vessel. Liquid is heated in an expansible vessel. Is that okay? Now, heated in an expansible vessel. The difference between the definition of apparent and cubic is that the cubic or volume expansivity, absolute expansivity, does not have expansible vessel when you are defining it. When you are defining apparent cubic expansivity, you have to put heated is in an expansible vessel. And don't forget this formula, real cubic expansivity equals apparent cubic expansivity plus cubic expansivity. We are going to solve problems with that. These are the parameters. We are looking for apparent cubic expansivity, which is for this. Real cubic expansivity is for the second one. If the linear expansivity of the material is this, and the density bottle holds is the mass, is the M1 250 gram. Okay. Now, why the other one? The mass M2 equals 248.5 gram, and the temperature theta 1 is 30 degrees centigrade, and theta 2 is 60 degrees centigrade. Now, we need to know the formula to relate together, and there's a formula to get the real cubic expansivity, which is this. We have apparent cubic expansivity plus cubic expansivity, and don't forget that gamma cubic expansivity equals to 3 alpha. You are going to multiply what you are giving linear expansivity by 3, which is 3 times 0.000006. Now let's get that. 0.000006 times 3. 3 times 6, 18. 1. And then add 0.000. And half goes to 0.000018 per Kelvin. Now, to get our apparent cubic expansivity, first question equals to mass of liquid expelled, mass of liquid expelled, that's the first thing that expelled from the container, over mass of liquid remaining, please, expelled is at the numerator, times temperature rise. That should be the case. Now, what we need to do, this water is in the container that holds as a 250 minus 248.5 divided by mass of liquid remaining. Let's see. When the temperature increases, only this and this. This is the one that remains. But to know the one that's left the bottle, you have to do subtraction. This one that left in the container after it has increased to this temperature. Now Now write 248.5 temperature, right? That's 60 minus 30. Okay, now do that. Apparent cubic expansivity. You do your subtraction. Do your subtraction very well. Over 248.5 times 30. What you need to do, make sure you multiply the down one with your calculator. 1.5 over. Let's do the multiplication so that you can see it together. 248.5 times 30. 0 times 5 is 0, 0, 0, 0. 3 times 5 times 5, 15. 5 carry 1. 3 times 8, 24, 25. 12, 14. Carry 1. 3 times 6 plus 1, 7. That's 5, 5, 9, 7. 1 times. Now 744, 7, 4, but we have 755.5. When you divide that, you have 0.0002012 per Kelvin. This is what you have, and as the apparent cubic expansivity as we have calculated before. Now we are looking for real cubic expansivity of the liquid. Now you have the real cubic expansivity equals apparent cubic expansivity plus cubic expansivity. And you have 0.0002012 plus what you have here, 0.000018. When you do addition, let's add them together. 0.00018, 0.0002012, 291200. You have that. Real cubic expansivity equals 0.0002192 per Kelvin. Both real, apparent, and all the expansivities units per Kelvin. Please let's take note. That's the end of our class. Please subscribe to my channel so that you can get the latest video. Have a nice day.